They line things up so that the processes are in a line, in a linear flow. So the material goes through it in a linear flow, with the idea being that from, receiving until shipping, or from start to end, a straight line is going to be the best path. They fail to take into account operator flow.
Thanks, Robert, for doing that. Thanks for being with us. I'm super thrilled to hear more about lean with you. If you don't mind, to introduce yourself and where you're coming from and what you're doing today.
My name is Robert Simonis. I'm the principal consultant behind KCE Consulting. That's KCE for Kaizen and continuous improvement, every day, everything, everybody. And I'm talking to you today from my home in Troy, Michigan.
Great, and we'll talk about circular manufacturing.
I wrote a short article that was published in Industry Week.
Yeah.
And kind of describes my a way of thinking. I was very taken with an article that had been published years ago about how this team was going into companies for mergers and acquisition activity. And just by walking around the floor, where they were able to recreate P&L pretty accurately. And it forced me to think. I was thinking, there's a lot of different tools I know to measure flow or calculate flow, whether that's operator flow with like time and motion studies, or inventory turns as a inventory material flow metric, time motion for how far stuff is traveling, et cetera, value stream maps, process flow maps, physical layouts. But I challenged myself. I said, without all the tools, without any data, how can I walk into a place and see flow? I know what it is, I know how to measure it, but how do I see it? And that got me thinking about how I can just see flow walking into a warehouse or walking into a manufacturing site, or really anywhere, whether it's the kitchen or whether it's a fast food restaurant. I started to look for some common things that would tell me whether or not flow was present. And that's, in a cellular manufacturing or even at the factory layout or warehouse layout level, that's what you're trying to achieve. I made up a set of rules, and they go in order. They're very specifically in this order, where one is start and end close together.
Right.
Are the start of the process and the end of the process close together? When I walk into a place and I see, receiving's on that side of the building and shipping's on that side of the building, right away I know they can't have flow.
Right.
Because even though material, the shortest distance between 2 points is a straight line, and that's great for material flow, which is the way I think a lot of people line things up. They line things up so that the processes are in a line, in a linear flow. So the material goes through it in a linear flow, with the idea being that from receiving until shipping, or from start to end, a straight line is going to be the best path. They fail to take into account operator flow. So if the operator is running a part or moving the material, then they got to come back. So it's not just a straight line. If they're not close together, they got to go to from the start to the end, and then they got to go back, whether they're on a fork truck or whether they're on foot, whatever. When really we want that start and end are close together, so that we can process, move, and then it ends, and then immediately we turn around and start the next cycle.
Right.
So start and end close together.
That's your first rule.
The first rule, what I call rules of the circle.
Okay, I like that.
And sometimes I abbreviate that to ROTC, but that may be an infringement on a group here in the States. But
probably.
But rules of the circle. The second rule was, don't cross.
Okay.
As soon as I have an operator cross themselves, it may not be a big deal, but what happens to material is wherever we cross, there tends to be a safety problem, whether we're crossing ourselves or whether we're crossing other people's paths. Certainly in a warehouse setting where we have machinery crossing the path of people on foot, or in factories where perhaps robots or other pieces of equipment are crossing people either on industrial trucks or on foot. But it's also the place where any kind of intersection, we've got to slow down, right? Just like you were on the street.
Yeah.
I come up to an intersection, I got to slow down to see who's coming from the other directions.
Yeah.
Perhaps I have to stop. At least I have to slow down. And it's where a lot of accidents happen. But it's also where material gets lost. Again, if I have an intersection, I have a choice of going straight or taking a right or taking a left. This is the point at which material gets mixed. It's where material gets lost. It goes the wrong direction. Perhaps it can skip a process step, things like this. So, don't cross.
Don't cross.
Because first is safety first. It's a safety problem.
Mm-hmm.
2, it's an efficiency problem. And 3, it's a quality problem. So for all those reasons, I don't want to design something where the material crosses itself, or the people cross themselves, or the crossing of 2 different people in their paths, or even 2 value streams. We want to have those value streams separated so they don't cross each other. So on all those different levels, don't cross. The third rule of the circle is make it smaller. So how do I I've lined up my processes, I've put them in some kind of semblance of, maybe not a circle, but circular, so that my process flow and my material flow should be the same. My operator flow probably is not the same as process flow or material flow. Another common mistake in cellular manufacturing is they think the operator has to follow the same sequence as the material flow or the process flow, and that's not the case. But how do I make it smaller? Again, in a warehouse, or in a factory, that could be physically moving process steps closer together, taking them out of process villages and making so that they follow the value stream rather than all the value streams or product lines going through goes through a set of stamping and then a set of welding and then a set of painting or assembly. And that may mean I have to right size the machines. It may mean I have to get clever about how to get things close together. It may mean moving where the power box and things like that are, so I can move machines closer together. In a warehouse, it means I'm probably moving the process steps, arranging them in the right sequence. In a warehouse, again, I can do things like slotting, so I can put the material I use most often closer to the front, so I don't have to necessarily go through the entire warehouse to get the parts I want. The parts I use the most are closer. Things like this allow me to make that. Again, the first and second rules mean that I've arranged the process steps. The material flow and the process flow are in sequence and they don't cross each other. But now I'm trying to bring them tighter together because less distance means less time typically, particularly when we're talking about cellular manufacturing, where I've got my operators going from one machine to the next. I don't want them to spend any time really walking. I want their time to be spent loading, unloading the machines and doing those assembly steps necessary to make the product. So to do that, I want everything very, very tight, very close. But that same principle applies on the next higher level at the factory layout level, or in some ways an entire warehouse is basically one giant cell. The operators are on fork trucks, but essentially it's the same methodology of making sure that the process steps are close together, the process steps are in the right order, and to minimize the total amount of travel for everything, right? For the material and for the people. Rule number 4 says it's not a circle, despite the name, right? I call it rules of the circle, and number 4 is it's not a circle. It's very common. The classic lean manufacturing is the U-shaped cell, where you start, it goes up, over, and back down. Start and end are close together. The U doesn't cross, and it's small, but it's not a circle. It's a U shape in the classic terms. Same with warehousing. It's very classic is to have like a Christmas tree shape where it goes in back and forth, back and forth, back and forth, back and forth, and then out. But again, the start and end are close together. The path is very irregular, but it doesn't cross itself. Another very common pattern is called the serpentine pattern. You start and you kind of make this snake move through it. But again, start and end are close together. It doesn't cross itself. So whether we're looking at traditional cellular designs for U-shaped cell, or whether we're talking about, very common patterns in warehousing, they follow the same rules. And again, I can see this. I can walk into a place and I'm thinking, where's the start? Where's the end? Are they close together? Do I see empty fork trucks going? Because if they're empty, it means where they started and where they ended aren't close together. Because if they were close, again, whether it's a pallet jack or whether it's a person's hands or whether it's a fork truck, right away, if I see these things moving empty, that tells me that either the process steps aren't lined up right or they're not close together. There's something wrong with the flow if they're traveling empty. Because if they properly designed, they'd put down and immediately they would pick up, or they pick up and then they put down close together so that as soon as I set one thing down, I pick the next thing up. Again, whether that's in a cell where you're talking a part, or whether you're talking a material handler or a water spider that's dropping off a full and picking up an empty, or whether it's a fork truck that's moving a pallet of material, setting it down, and then picking up a pallet of material and moving it to the next whatever, the next station, the next process, the next whatever. But by design, those start and ends are close together, and you can see it really easily when things are moving empty. Again, whether it's hands, whether it's a pallet jack, whether it's a fork truck, you see those things if they're empty. And the funniest thing is when I see one fork truck going this way empty, and then I see another one going that way empty. It's like they really haven't thought through what they're doing, because they got people going both directions empty for one reason or another.
So the 4 rules of a circle again: start and close.
Start and end, close together.
Close together. Number 2, do not cross flow. Number 3, make your circle smaller. And number 4, circular but not circle.
Right. It's not a circle.
It's not a circle.
And again, there's reasons that if it were a true circle, it's really not the best it can be, because when you get that U-shaped cell, when it's a circle and I'm trying to do that line balance, now I got a couple steps from one side of the circle to the other. When it's that narrow U shape, I can line balance across the line with just a step or a step and a half.
Right. So
that's why it's not, again, it's circular, but even if it were a perfect circle, that's not the best shape. The best shape is not a circle. And again, all the typical examples, the U shape, the serpentine, the Christmas tree, etc., are not a circle, but again, circular.
Circular.
Yep.
All right. Well, thanks, Robert, for doing that. Very instructive.
Absolutely.
going back to your first rule, why do you think people tends to design lines when we're talking about assembly lines or sub-assembly lines, or why do we go back to this having a straight line? Do you see a pattern there of what people are doing? Or
Yeah, I mean, there's a variety of reasons. One is the idea that assembly lines, where you line stuff up and people are static, they're standing still, so there is no loss because they're standing still. And again, the shortest distance between 2 points is a straight line. That's one reason, and I'll come back to that in a second. The second is just tradition. I mean, I think it's very traditional way of looking at it. And again, if you're thinking of process steps and you're thinking of material flow, straight lines make perfect sense. It's only when you start to think about operator flow, whether that's an operator on a fork truck or an operator doing assembly or manufacturing, whatever. And to be quite honest with you, I see very, very few layouts, either at the cell level or the factory level or warehouse level, or even at a larger scale. You know, I've seen some of these maps looking at all of North America and movement between Canada, Mexico, and the US. They're not thinking about the flow. They're thinking about the pieces or the process sequence or the material sequence. They're not thinking about flow. They're not thinking about the movement. Or if they're thinking about movement and flow, they're only thinking about material flow or process flow. They're failing to consider how not having the start and end together means that my operator, again, whether that's on foot or whether it's on a machine or whether it's in a semi truck, they got to come back, and they're going to come back empty if I don't plan for a load to come back with. So I see lines a lot, and the only this idea that people credit Ford with, this idea of creating the assembly line, and each person on the line has a very, very specified task, and they just do that one task, thousands of repetitions of time every day, is a concept and idea that's very well ingrained, and I think I don't know, it just feels natural to do it that way.
Yeah.
And again, in traditional industrial engineering, when we talk about line balance, well, first they'd say, okay, walking is waste, right? We don't want to spend any cycle time in walking. I understand that, because if I got one machine here and one machine here, the guy's going to do a little work here, he's going to walk, he's going to do a little work here, and then walk back. And it's easy to spend half your day walking, and then I got to charge you a gym fee and give you a t-shirt and that stuff. We don't want it to be an exercise program. We want it to make parts. So we want to take that walking out. And so the solution for Western engineers was to create a static position where the operator stands still and the work comes to them. So whether it's by conveyors or slides or fork trucks delivering pallets of material, the idea was get rid of the walking, because walking is taking too much time, and we'll bring the work to the worker. And now I want to load that worker at 92% capability, whatever. And the solution was to have what they call line balance, so that everybody's now static, and I want to make sure everybody's running at about the same cycle time so that parts will go through. When they're in a line, I can only shift work to the right or the left. I can take, if this station is got more work than the other stations, I can take some work from here and move it to the station before, or move it to the station next in line. Or if this station is faster than the other stations, again, I can move some work from the station on the right to it, or I can take some work from the station on the left and bring to it. And that's really the only way you can line balance.
Right.
the situation in other parts of the world was different. They didn't have the volume needed to really make that kind of system work, so they came up with a different system. And instead of saying, I don't want people to walk because it's taking too much time, they thought, well, they have to walk because I got all these little machines. I don't have a 400-ton press. I've got maybe a series of little presses or hand tools or whatever. So they're going to have to walk. Now, how do I make it where, and instead of the choice of you're walking or you're working, how can I do this where they happen together, where you're walking but you're working at the same time? And the answer is you put those processes very, very close together, 30 inches or 0.8 meters apart. Why? Because that's one step. Every step you're at the next, physically every step you make is the next step in the process. So the machines are designed to be, again, 30 inches wide or less, but typically 30 inches, 0.8 meters, so that every step I'm at the next machine. Now, that might mean they're very, very deep.
Okay.
And in some cases, very high, though they try to keep them where you can see people's faces.
Right.
That machine might be very, very deep, but it's very narrow. So for the operator on the inside of that cell, okay, so it occupies, 100 square meters or something. So what? To them, it's less than a meter wide. It's 30 inches wide. It's one step. And again, a lot of machines, they have like the electrical panel is on the side of the machine. And depending on what state or country you're in, there's a requirement that you have that electrical panel, have access to it, and you've got to keep 30 inches or 36 inches or 1 meter clear,
Right.
so that in an emergency you can access that panel. Now, if I want to put machines side by side by side, I've got to design those machines where I can do that. So to make a cellular manufacturing cell, right? To make a lean cell, I need lean machines. I need machines that are designed or can be retrofitted to where they can be literally side by side, which may mean I put the electrical panel on the back of the machine. Still meet the legal requirements. There's access back there, but again, from the operator's perspective, it doesn't matter. One, that machine is 30 inches wide, and the next every machine is 30 inches wide or 20 inches wide. For the maintenance guys, they have access from the back to any of those things. Again, same things with where do you put the oil in, where do you the service panel. Those things are typically arranged to where they're accessed from the back, and free and available for the maintenance and technicians to do things without interfering with the operator. But again, now I can put those machines side by side by side.
One of the main point I think we're going to say is that the operator now can switch jobs with the people not only on the right side and the left side, but also behind, or
right. Once you're in that, again, when it's very narrow, a very narrow U shape or some other shape, call it a T, call it whatever you want, but if it follows those rules, where start and end are close together, it doesn't cross, it's small, then by its nature it's circular. It may not be a circle, but it's circular because it meets it's the same definitions of a circle, right? Here's my circle. It doesn't cross itself. Let's assume this is small. And again, is there a start and end? Truly in a circle, there is no start and end. It blends from one to the next with no transition. So when we're talking about line balance now, and again, instead of having the solution where I've made a station where an operator is standing or sitting and the work comes to them, and which led to more and more integration of this one station so that you can do multiple jobs in this one station or multiple kinds of work. Instead, we have lots and lots of little machines or discrete pieces that are very, very close together. So now, and because it's very narrow, again, the typical path, if this is an operator cell, if it's one operator, again, it's that same 30 inches. If it's two operators, maybe it's 36 or 42. There are some legal requirements depending, again, what state and country you're in that says, the minimum width of a aisleway. In the U.S. is typically 30 inches or 36, depending on the state. Some other countries have other regulations, but it's rarely more than a meter for two operators to be in that cell.
Do you think that the machine design or the acquisition of a new machine or a new piece of equipment is one of the challenge? Because it's, I'm guessing that the upper management will...
Yeah, it's not insurmountable.
Okay.
Depending on the kinds of machines that are currently in a place. But certainly if I was in a greenfield, if I was designing something new, I would want to make sure to be thinking about that as a design criteria, whether I'm buying new machines or whether I'm buying machines, new machines, old machines, whatever, or whether I'm designing machines or giving characteristics for a machine. These things would be part of my design criteria. In existing machines, it might be a retrofit, or in some cases not necessary. Again, it really depends on, a screwdriver on a workbench doesn't need any redesign. But perhaps some custom equipment would require either redesign or initial design. And again, if I'm going to design a machine anyway, I might as well design it for the cell, whether or not it's going to go into a cell or not. But we were talking about line balance, and once I have many small pieces of equipment, as soon as because they're just a step or step and a half apart from each other, from this side to that side, but also one step apart this way, it allows me to do line balancing. I can combine it gives me tremendous flexibility because I can combine different elements, not just to the right or the left, but to the right, the left, and behind at an angle, and behind at that angle. I can now combine different tasks in many, many different ways. So if I'm making a mix of different kinds of parts, perhaps some parts use a process that others don't, or this piece has 12 screws I got to do, and this one's got 4 screws. So the cycle times are different for the different builds. This one's got more content than that one. It allows me, depending on the mix and the model, whatever, I can reconfigure. I can line balance for every different job, every different time, in multiple different ways. So it's tremendously flexible. I can add process steps. I can take out process steps. I can swap individual machines. All these things you can't do when it's all integrated into one station.
Now, how do you sell that to the worker? Now you'll have to tell him, okay, you'll have to learn 3 other new tasks. Because I'm guessing that there might be reluctant to that.
I've had the opportunity to do this in 15 different countries around the world. In every country I've been to, I hear the same answer. I'll show them videos of from some operation, and they'll go, "Oh, well, that's that country. We don't do it here. We don't work like that." Yeah. And then they start doing it, and they realize how much better it is. And I'll show video of them to the next person, and the next person, "Oh, no, that's that country. We don't work like that in this country." So I always get the same response.
But you don't need to change country to hear that. It could be the industry or the company. Just
right, right. But quite honestly, I'm very, very hesitant to show people videos of how it works, because to the outside eye, it looks like a heck of a lot more work, because they're moving, because they're doing multiple tasks. They're like, "Whoa, today I just sit here and do the same thing 10,000 times. Now you want me to, do 7 different machines and do 7 different actions." And
exactly.
And it looks scary. It looks like a lot more hard work. But how do you sell it to employees? The best way is to get them to do it, either in a full-scale mock-up, or if the equipment and layout allows it, physically rearrange things and let them try it, because it's scary to see it, but to do it, they start to realize, what, this is a lot. I like this better. That's the comment I typically hear.
Really?
And a classic was this operation down in Texas. It was a union facility, automotive industry. And we set up some cells from existing machines, and the existing processes were a lot of people sitting down doing the exact, you're putting a piece of metal in this fixture as it goes by you on the conveyor line or something like this. And we made these cells, and according to the union rules, if you've got the seniority, you don't have to do the job. You pass it down to the lower seniority person. And so there was one person who had a lot of seniority. They said, "Well, I'll try it. And then everybody else that was in the cell, and it was like a 3-shift operation, everybody else in the cell was like the junior most people in the factory. I came back some 3 months later, and all the people in the cell on every shift had like 24 years, 25 years, 26 years of service. All the very senior most people in the union were now in that cell, because the one guy that had seniority was doing it, and he started to talk about how much he enjoyed his work now. And so somebody else tried somebody else. Pretty soon they're like, make the young guys, make the junior guys sit there all day doing this all day, because that's boring as hell. I don't want to be bored. But for lots of different reasons, right? So one guy tells me, it used to be I'd go home from work and I'd be so tired I would fall asleep at the dinner table. He goes, "Now I get off work and I go out bowling."
Okay.
Ergonomically, if you're up and walking around and you're doing multiple tasks, instead of doing the same motion 10,000 times, perhaps now you're doing a series of different tasks, and maybe you do them a couple hundred times in a day's time. Mm-hmm. But ergonomically, walking keeps the back straight. Well, not straight. It keeps it in the S curve that it's supposed to be in. Using different muscle groups throughout the day allows, instead of doing just one motion 10,000 times, and at the end of the day, my shoulder hurts, my elbow hurts, my wrist hurts. Well, now I'm doing a little bit with a lot of different muscles. Physically, you're not as tired, but even more tiring is boredom. Boredom will make you feel way more tired than the activity, right?
True.
So they're sitting there 10,000 times, they're putting this metal plate on the fixture as it goes by. Now they get to see the start, the beginning, and the end. They get to see the part completely made. and they know whether it was a good part or a bad part.
So you're
One, they
saying,
find,
yeah, sorry, you're saying that you would say to a manufacturing engineer, you need to have them test it out first, and they'll just love it, dude. But that's, I guess, the
well, love it is a pretty strong word, but
okay.
but if I show them what it looks like, it'll be scary. You will scare people away. It's much better to work with them, to develop the cell, utilize their ideas because they're already the ones doing it. But also by doing it, they'll realize that it's not as scary as it would look from the outside of the cell, right? By being in there and doing it, you get in a routine. And again, the sense of ownership. When I'm putting this thing on there 10,000 times a day, were they good parts or bad parts? Don't know. You know, what's my motivation? My motivation is not to get fired, and I sit here and I put these things all day. One guy told me, he said, Robert, before I was always looking to see where the supervisor was. Now I don't care where he is. You know, I was afraid where he was because I had to look busy. Now I am busy and I don't care where he's at. You know, another guy told me, man, that clock used to run so slow. Now the day just flies by. But the biggest thing was the feeling that before I didn't know whether I was making a good part or a bad part. You know, there was no feedback, nothing. Now I know whether or not I made good parts, and I feel good about making good parts.
Yeah.
You know, I take pride in my work.
Yeah.
Before, what pride in your work can you take when your job is to, you know,
Quantity.
put this metal flange on a bracket? It's so they enjoyed their jobs. They felt much more connected to what they were doing. They got instant feedback. Again, they didn't have to wait for some kind of report or productivity report or efficiency report or scrap report. They knew immediately because they were the ones making the parts and testing the parts. They knew whether or not it was a bad part right away. And it engages their mind, how to fix it, etc. They just enjoyed their job a heck of a lot more.
Right.
So yeah, don't show them what it looks like in a video because that will scare them. Because standing back, you're going, man, that guy's just flying. That's crazy. But to do it is a whole different experience. And people are again, routinely, I get this feedback that, you know, I'm not bored anymore, or I really like this. I like knowing that I made good parts. I'm not as tired at the end of the day. Again, if work is calculated in calories burned, yeah, they probably did more work, but it's more evenly distributed through the body. They're walking. Again, when you sit, you tend to have more back injuries, more shoulder injuries, more elbow injuries. Same with standing still, you get more knee, hip, back injuries. When you're moving, there's a lot less injuries. So again, just physical exhaustion, both from the boredom, but also from you're working one muscle group repetitively instead of the entire body. They're feeling more energetic when they go home at the end of the day. They take pride in their work. They're enjoying their work. Yeah, don't show them the video because that'll scare the heck out of them. But work with them to design the cell, and people are pretty routinely much more engaged in the work, much enjoy it a lot more.